Okay, today I'm going to talk to you about freezing point depression and a little bit about osmosis, and that will basically wrap up our chapter 12 material, which means you can expect an assessment of some sort next week. Remember, we do not have school on Friday. So probably Tuesday, Wednesday of next week, you can expect an assessment. I will put together the details on that. And then when I know the details, you'll know the details because, again, this is kind of uncharted territory for me. So just be patient with me on that. I won't throw any surprises at you. You'll have plenty of notice in regards to how that's going to proceed. So I'm going to pull up my notes for the last part of chapter 12. Oh, hang on. Let me show them to you too. Let me present them. All right, so the last little bit is on freezing point depression. Well, when you add solutes to a solution, in most cases, at least a liquid solution, you're going to lower the freezing point. You elevate the boiling point when you add solids to liquids, and we depress or lower the freezing point. The formulas are going to look similar, and the constants you're going to be able to look up on the chart just like you would with boiling point depression or boiling point elevation. There's also tables for freezing point depression regarding the constants. Same kind of idea here. There's the constant. Look it up in a chart. All right, so we're going to use that same change formula. You take the new, subtract the original. There's your delta. There's your change in temperature, freezing point. Okay. Again, we're going to use molality in these calculations. And we can also, in order to find that change in temperature, if we don't know the new and the original, we can look to our molality calculations and going back to the constants that I mentioned that are there for you. You don't have to know the constants. Now, why do we care about freezing point depression? Well, it helps us a lot, actually. Here, we don't have super, super cold winters, but we can have spells where it can get cold. And what do they put on the roads when we expect ice or snow coming along? They put sand, of course, but what else? Hopefully you're thinking salt. And that's what the reason they do that is because when you add salt to, in this case, frozen water, even though the temperatures stay below freezing, that salt actually lowers the freezing point of the water, the ice, and that allows the ice to be able to melt at lower temperatures than the 32 degrees Fahrenheit or 0 degrees Celsius. So the salt lowers the freezing point, and so it actually melts at colder temperatures than it normally would. So that's why it's important. Antifreeze does the same thing. You have antifreeze in your cars too, and that keeps the water in your cars and the tubing from freezing. And then the problem with that is if water freezes in your car, it's not doing what it's supposed to because it's basically staying put, taking on the properties of a solid, but also it expands. And that causes real problems with the capacity and the volume that the tubes can hold. So antifreeze is good. Salt on the roads is good. Now, I'll tell you, that they use a couple types of salt generally when they put salts on the road. Now, I want you to think about why based on our boiling point elevation discussion. All right, so they use calcium chloride and sodium chloride, both. Which one do you think might have the greater effect? Calcium fluoride, which has a formula of CaCl2, or sodium chloride, which as you know now is NaCl. Which one do you think might have a greater effect on lowering that freezing point? What do you think? All right, I'm going to assume you knew the right answer. And I'm going to assume that you knew it was CaCl2 because when it dissolves in water, it forms 3 ions, 1 calcium, 2 chloride, as opposed to NaCl, which just forms the 2 ions, Na plus, Cl minus. Okay. But your book goes into quite a bit of detail on pages 324 and 325 about this, and it gives you actual temperatures that can be used that we know. But so if you think about this, if you put antifreeze in cars, it will depress the freezing point by about 12 degrees Celsius. So temperature can go down to -12 if the freezing point is 12, or excuse me, if the freezing point of water is 0. It can take it down and make it so that it won't freeze until you hit -12 degrees Celsius. So that can make a big difference in some places. And then some places that's not enough, and people take extra measures. If you live in really, really cold environments, you put heaters in your garages, for example, because the cars would get too cold regardless if they were not heated. But that's a different story and why you don't want to live in Wisconsin. All right. Now, we're just going to jump into problem solving similar to what we did with boiling point elevation. I'm going to go through a couple of problems with you, and then I'm going to assign you a couple. You're not going to have that many, maybe 2 or 3 to do with this assignment. And again, you're going to use table 12-5 on page 324. That's going to have your constants and your freezing points for a handful of solvents. All right. So here we go. We're going to use naphthalene again, but instead of acetone like we did before, we're going to use phenol. All right. So how much will the freezing point of phenol change if 4 moles of naphthalene are dissolved in 2 kilograms of phenol? So naphthalene is a covalent molecule, so you don't have to worry about it breaking apart like the ionic compounds do. So you don't have to worry about the ratios there, and if you have to have particle molality, because you don't. So you can just assume that 1 mole of the particle, in this case, or substance, in this case, naphthalene, you're going to get 1 mole. Okay, so you don't have to worry about that. So go to molality first, because we're going to ultimately use this formula down here. So 4 moles of naphthalene divided by the mass in kilograms of phenol gives you 2 molal. That's the molality of that solution mentioned in the problem. But the question is, how much will the freezing point of phenol change? So we're actually just solving for the delta value here. So we go to the table. I want to do that right now in my book, and I'm going to look up phenol. And I see that the phenol has a K sub F value of 7.4. So I'm going to fill that in right here. Again, that would be given to you on any kind of problem set, or I would tell you to go look in the table. And then you would have a 2 molal solution. So your change in temperature is going to change that freezing point by 14.8 degrees. Now I'm going to go back to that table, and I'm going to look at phenol, and the freezing point of phenol is 40.9 degrees. Okay. So this is going to change. Somebody do that math for me, actually. I don't want to embarrass myself. I'm actually going to pull out the calculator, and that might be embarrassing in and of itself. So the freezing point is actually going to be 40.9 minus 14.8. So you get 26.1 degrees would be the new freezing point of phenol if we added that that molality of naphthalene in it. Okay, now let's look here. One more problem. So compare the freezing points of a 3 molal calcium chloride solution and a 3 molal NaCl solution. So notice that is 3 molal of CaCl2. Now we're going to assume this dissociates in the solvent. And calcium dissociates into 3 ions. Look at these subscripts, 1 and 2. So you're going to get 2 calcium ions for every 2 chloride ions, excuse me, for every 1 calcium ion. So a total of 3. So I'm going to take the molality, 3, and then multiply it by 3, because I want to have 3 ions. 3 times 3 is 9 molal. Then I'm going to come over here to my sodium chloride, and I'm going to double it, because when NaCl dissociates, it forms 1 mole of its sodium ions, 1 mole of chloride ions, and so that would be 2. So 2 times 3 is 6. So those are the molalities I need to use. And then I'm going to compare. Let me do a subscript here. All right, so my change in temperature for CaCl2 is I'm going to go back up to my triple molality and then multiply it by 1.86, which is my constant, my freezing constant, my freezing point constant, excuse me, for water. And when I do that multiplication, I get 16.7 degrees Celsius. All right, so what that means is I take the freezing point of water, I subtract by how much it's depressed by, which is 16.7, and that would mean if I added that molality of calcium chloride, I would get a new freezing point in my solution of negative 16.7 degrees Celsius. Now, this is the type of salts they would use to put on roads to keep them from freezing during the winter when we're having a snow and ice storm, or to help melt the snow and ice faster. So the same thing for NaCl, except we doubled it, but we're still talking about water. So we're going to take that constant and multiply it by 6, because that's the doubled molality. And let me fix that. Okay, so when you do that multiplication, you get 11.2 degrees Celsius. Then I subtract the normal freezing point of water minus how much it's depressed by, and 11.2 degrees Celsius is what the freezing point would be if I put that molality of salt solution on some ice. Okay, so it would freeze at 11.2 degrees below zero with that molality of a NaCl solution. So with using calcium chloride, the temperature can actually drop 5.5 more degrees before it becomes ineffective to help melt that solution. All right, so the last little bit here deals with osmotic pressure, which deals with a little more biology than it does chemistry in some respects. But it does deal with the way particles and solutions work. So we're just going to hit on it for just a moment. So osmosis, if you remember from biology, those of you who have had the life science course in middle school, that's the process in which a solvent moves across a semi-permeable membrane. Namely, since we're biological creatures, we're talking mostly about water. And your cells have a semi-permeable membrane. So water comes in and out of the cells depending on the environment in which your cells are in. So if you, and water's job is basically to dilute until both sides on both sides of the membrane are relatively equal in their concentrations. So eating salty meals will affect the way that semi-permeable, how much water goes across that semi-permeable membrane, just for temporarily anyway. So when we deal with osmosis, there's a pressure involved. So the osmotic pressure of a solution is the amount of pressure required to prevent osmosis from occurring. So the more solute particles you have in a container, the more water or whatever the solvent is, the more that solvent wants to do its job. And the solvent views its job as diluting that solution. So there is going to be a buildup of pressure because that water, in our case of our cells, for example, wants to gush out and dilute whatever particles are in a higher concentration. It wants to take care of that problem. It wants to reach equilibrium again. So there's going to be a buildup of pressure for that solvent, water, in the case of biological creatures. There's going to be a desire to get water to the where there's the more solutes so that water can do what it's supposed to do in the case of dilution. So a few terms just to keep in mind. A hypertonic solution means it's more concentrated. Hypotonic means it's less concentrated, and isotonic means there's an equal concentration. So here's how I think about this. The concentration of solutes inside a human cell is about 0.3 millution. All right, so inside your cells, if you have basically reached, everything's normal, homeostasis is established, your cells have a 0.3 molar solution. Now, if you were to take that cell or do something, eat something, drink a lot of water, drink water, whatever. If you are to generate outside the cell a hypertonic solution, remember, go back here, hypertonic means more concentrated. Which way do you think water is going to want to flow? Okay. Hypertonic means a cell is placed in a solution where the solution has more particles than the cell. Water wants to leave that cell to dilute the solution. So water is going to leave the cell, and if enough of it leaves, that cell is going to shrink because it's going to have lost so much water. Conversely, if you place a cell in a hypotonic solution, meaning the cell has more solutes than the solution it's resting in, what's going to happen? Water is going to go into the cell to dilute the cell's solution. And then at that point, if there's too much of a discrepancy, those cells are going to take in so much water that eventually, in theory, they could burst. All right, then if you place that cell in an isotonic solution, that means it's equal across. And so water is just going to flow nice and easy back and forth with no pressure at all. Doesn't really need to be either place. It's just going to flow nice and easy back and forth. Okay, now that's the end of the notes. Hooray, yes. So I'm going to post this in the video, so you need to watch. Obviously you have, so I'm glad you've watched the video, and then I'm going to post a few questions. It's not going to be a lot, 2, 3, maybe 4. I had to look through it a little bit more carefully as I stop this recording. But those will accompany this assignment. And then on Thursday, you will have, we'll talk about solubility and solubility graphs. But it'll be a different kind of notes. It won't be these problem-solving notes. We'll do some stuff with solubility graph, which you'll find out more about on Thursday. So I hope you guys are doing well, and I will talk to you online.